Good afternoon and welcome to our final lecture on fluid mechanics. I hope you all had a chance to download the slides and then get ready for today. So as I said, today is the final lecture. Let me switch over to the slides to show you what we're going to do today. Here we are. So today's lecture is called the Repetitorium, and as the name says, we're going to repeat all the things, to a certain extent, all the things that we looked at in the past 13 lectures, right? In total, it was 13 lectures. I will not say a whole lot about the last two lectures, experimental fluid mechanics and computational fluid dynamics. These were kind of special lectures, not a classical formal frontal lecture. And I will mostly focus on lecture 2 throughout lecture 11, which are classical fluid mechanics lectures. During the whole lecture, I will try to sketch here on the blackboard an overview of the whole course material, which should somehow connect the different topics and give you, let's say, the big picture. Now, the blackboard in my back is relatively small, and I will probably not be able to write down everything I want to write down. So what I have done, I have uploaded a photo of what I'm going to write on the blackboard from a previous class. This is a printout. You see, it's like a large-scale blackboard we have usually in the lecture halls. So please download also this this photo of the blackboard. It has a few more notes on it that I will not be able to put on the blackboard. Yeah, there's also numbers on it, but be careful, the numbers on this photo are not consistent with the schedule. Right? But don't worry too much, you'll see as we'll go on. Okay, so a little outline for today. Main topic, as I just said, review of our studied topics, summary of 13 lectures of fluid mechanics, everything you ever wanted and needed to know. Well, maybe not needed, but maybe more than you ever wanted to know about fluid mechanics in 13 lectures. Then we will take a little break for course evaluation. I hope all of you have received an email from the university with a link for the course evaluation. I will give you 10 minutes of time to complete that. And then the last third point of today is some slides, some information about the oral examination. You know that due to Corona, there will be no no classical written exams as we usually do for this lecture. It will be online oral, so we'll use Zoom to do online examinations with each one of you separately. And well, it requires a special organization, and that's why I would like to talk to you about this, give you some background information, also give you some information what I expect from you. We're going to look at an example question on that. Okay, but that toward the end of today's lecture. There will be no exercise lecture because there's no exercise left. Kai, nevertheless, he's here with us, and he will stay online after this lecture. So you'll get a chance to ask him some final questions, just to, well, whatever comes up, he will be there, and you can talk to him. Otherwise, if questions come up during the repetition, during this lecture, please, as usual, write your comments or questions on the chat. Kai will try to answer them. Maybe I will also try to answer them during the actual lecture, because I think in this context we're really repeating. It should have time, and it will have time to dive in more deeply into things that you feel you have not sufficiently well understood. All right, so now I said a lot. Let us just start with the actual content of today. So review of the studied topics. In the very first lecture of this course, I first started with some things that I thought were motivational examples or gave you an idea of what fluid mechanics is all about. But already there, we dove into quite a complex, or at that point, probably a relatively abstract topic, and it was the topic of non-dimensionalization, or let's say, of dimensional analysis. We looked at the Buckingham pi theorem, made a few examples, and we already derived one of the most important non-dimensional numbers there, the Reynolds number. And over the whole course of the different lectures, we came back to this Buckingham pi theorem. And I hope somehow deep inside your head, you understood now that the power of this concept of Buckingham pi, of dimensional analysis. Now, I will certainly not make this topic of an exam question, but certainly all dimensionless numbers and the value of a Reynolds number in particular certainly may be one of the things we will talk about during the general exam. But the real classical lecture format started only with the second lecture, where we went into flow kinematics. Now, flow kinematics, maybe at that point it was not so clear to you, but by now it should be clear to you that in flow kinematics, we did not really solve any conservation laws. We did not solve any governing equations of fluid mechanics. We just developed a mathematical tools, or let's say mathematical concepts of describing a flow. One of the main things I tried to explain to you in this lecture was the difference between a Lagrangian and Eulerian description of flow. Lagrangian descriptions of motion, of fluid motion, or actually of motion of any mass particles, is something which is quite common and quite intuitive if you deal with, let's say, rigid body dynamics, cannonball flying through the air, or even dust particles settling. This is a classical example where Lagrangian description makes a lot of sense, and Lagrangian description is used. So that's what you usually do in classical, let's say, high school physics, mechanics lectures. Now, the Eulerian description is something that is really well suited to fluid flows, especially well suited if we have a continuum, which we consider the fluid to be one. Fluid, in the way we deal with fluid, is not considered a set of different mass particles, but it's a continuum of mass with certain density that can move. That's why we use the Eulerian description. And in this lecture, we tried to switch between the two descriptions. And one of these, the results that came out of that was actually the substantial or material derivative. That's the acceleration of a fluid particle in Eulerian description, the Lagrangian acceleration of a fluid particle or a mass particle described, whose motion is described in a Eulerian way, written in mathematical terms. We also looked at streamlines, streak lines, path lines. Word of caution on the streamlines, that streamlines, if they're used for a non-steady flow, that they can be very misleading. And then we introduced two additional concepts which are quite important. Next to the classical velocity field, which is an obvious thing to do, pointer next to the velocity, we also introduced the vorticity. And vorticity is something that we sometimes looked at, like when we looked at boundary layers, we saw that there's a lot of vorticity inside boundary layers. If we go to the outer flow field, potential flow, we saw there was no vorticity. And the third concept was the stream function. Stream function, which allows us to describe a whole velocity field. Like in 2D, it has two velocity components, u and v. We can describe this velocity field, this vector field, just with one scalar function. A very convenient tool, and we came back to the stream function in the context of potential flow, where we saw that somehow there's a certain duality with the potential, the velocity potential of an ideal flow, of an emissive flow. Okay, so this is essentially what we did on flow kinematics. And let me now go to the blackboard and start off with our sketch on the blackboard. So start here. And we're going to start off with the title on top, which is called fluid mechanics, obviously. And the very first item that we want to add to the sketch, so from fluid mechanics, we're going to branch out and make all these definitions: compressible, incompressible, viscous, inviscid, and so on. But what we did in the very first lecture, or sorry, in the second lecture, was flow kinematics. And this was lecture number 2. So that's what we're going to use these numbers for. Already at the very beginning, we made the decision, or I told you, that we're going to deal 80–90% of this whole course with incompressible flows. So the first distinction we're going to make is incompressible versus compressible. On the other side, we have the compressible branch. This is one of the first distinctions that we made. And actually on the incompressible side, we made a lot more distinctions. Another one was inviscid or viscous. And when I say viscous, I should actually clarify that we only looked at Newtonian fluids. If you look around in nature at all kinds of viscous fluids, you will find that there's quite a few fluids which are not behaving as Newtonian fluids. Blood, for instance, is not perfectly Newtonian. However, in many, many cases, it can be safely treated as a Newtonian. And we just decided, for simplicity, but also for practicality, to only look at Newtonian fluids. Newtonian fluids means we're dealing with fluids where the shear stress is proportional to the velocity gradient. Let me make that note here. When we say viscous in this lecture, we implicitly mean Newtonian fluids. Newtonian meaning tau is proportional to du d1. And the proportionality factor is just the viscosity, the dynamic viscosity. Okay. So these were some very initial distinctions we made: compressible, incompressible, incompressible, viscous, incompressible, inviscid. Let's see how we went on with that. Let me switch back to the slides here. Yes, that's what we started when we started in lecture number 3 with conservation laws for incompressible flows. The first law we looked at was the law for conservation of mass in a 1D flow, or let's say a flow along a streamline, just because to get a basic understanding, it was sufficient to look at a 1D flow, and if we look at incompressible flow, it makes our life easier in a conceptual but also in a mathematical sense. To understand mass conservation in a 1D or in a streamline flow, this picture was sufficient. Actually, we used the same picture later on in the lecture on compressible flows. The only difference was this row here, row 1 and row 2, was either a constant or it was a variable in compressible flows. But very quickly we could formulate a law for mass conservation. And in a second step, we formulated a conservation law for momentum, Impulsgleichung, Impulshaltung. If we neglect viscosity, and that's what we did in the first place, if we neglect viscosity, we came up, or we ended up with Bernoulli's equation or Bernoulli's law. Bernoulli's law, this famous simple formula, which tells us that the sum of a few quantities is constant along a streamline, as long as you don't have viscosity. If you have viscosity along the streamline, you will lose some of this constant. And that's an extremely powerful law with all the limitations it has, but it's a very powerful law. And we used it throughout the lecture again and again to get an understanding of how pressure is changing and how, for instance, measurement devices can be designed like the Repetitorium. So Bernoulli's equation was one of the first important results out of a lecture on conservation. And if we look at our tree now, we have to follow fluid mechanics, incompressible, inviscid, and for the case of 1D, one-dimensional flow, we end up with Bernoulli's law. And that was essentially lecture number 3, or the first half of lecture number 3. In the second half of lecture number 3, we extended our concept from 1D to 2D or 3D flows, and we started including viscosity. So we're on this side branch, we're at the viscous equation. And one of the things, or the major result we got here, was the Navier-Stokes equation. So also that was lecture number 3, Navier-Stokes. And here, continuity equation, which in incompressible flow essentially means that the divergence of the velocity field must be 0. Momentum equation, well, that ended up being the Navier-Stokes equation. We also looked at the non-dimensional form. And if we choose the proper reference length, reference velocity, reference timescales, we end up with a formulation which contains the Reynolds number in it. Or if we have an unsteady or a pulsatile flow, we have an equation which contains the Reynolds number and the Womersley number. So we had two non-dimensional numbers appearing automatically in the Navier-Stokes equation again, something we already derived in the first lecture in the context of Buckingham. All right, so let's continue. Here are the conservation laws written down again with the two, maybe the most important non-dimensional numbers that we had in this whole course. These are by far not the only ones that exist, but it's the most important ones that we came across. And I'm certainly expecting you to understand how to write down these equations and what they really mean, what the concept is, and to estimate values of these non-dimensional numbers for certain applied problems. All right, so we had the basis for studying fluid mechanics. We had flow kinematics, how to describe a flow, and we had the conservation laws, how to calculate the flow, what equations to solve. So we went into lecture number 4, and lecture number 4 was the lecture where we actually solved the conservation laws. We made no simplifications. Maybe we made some idealizations. Usually we assumed like infinitely long structures or perfectly flat plates moving parallel to each other, like what we have here. And we found out that in these idealized, or very often people also talk about canonical situations, canonical configurations, we can actually find exact solutions to these rather complex partial differential equations. Especially in the case where two plates are moving against each other, we obtained a surprisingly simple Couette flow or plane Couette flow solution, which is just a linear velocity profile, and it's an exact solution of Navier-Stokes. And if we have the two plates not moving against each other, but we have something pushing, or let's say we have a pressure gradient along the length of this channel, we obtain a Poiseuille flow, a plane Poiseuille flow, not to be confused with a pipe Poiseuille flow. It's a plane Poiseuille flow, but has a parabolic velocity profile. So this is a parabola. And we also found that these two solutions can be superimposed to get this mixed solution. We also looked at the flow between two rotating cylinders, inner cylinder rotating, outer cylinder rotating. And we also found that there's a surprisingly simple, analytically correct, exact solution of Navier-Stokes. And I think that was really important. We looked at two extreme, or let's say degenerated cases, namely one case where the inner cylinder degenerated to a cylinder of 0 radius, actually disappeared, and we just had the outer cylinder rotating, and we ended up with a flow which is like a solid body rotation, right? Essentially, this is what's happening if you rotate a bucket of water for a long, long time, such that everything moves like a solid body. This solid body rotation, or this fluid flow, which looks like a solid body rotation, has vorticity, and this vorticity is, of course, related to the rotational speed of the bucket. The other extreme was obtained when we took the outer cylinder and let it go to infinity. Right? We let it grow infinitely large, and at the same time, we made it stop, so not rotate anymore and get infinitely large. So we just have the inner cylinder rotating, and we ended up with a solution which looks like that. And it's a vortex which, surprisingly, although it's rotating, it's a vortex, it has no vorticity. It's a bit of a mishap that these two words sound almost the same, a vortex and vorticity, but there are vortices without vorticity. And it's exactly that vortex, which is called an ideal vortex, which later on we learned it's also a potential flow solution vortex, is a vortex without vorticity. Okay, so these are some of the results that we obtained in the lecture on exact solutions. We also looked at the exact solution for flow through a pipe. We didn't really derive it, but it would have been very, very similar to the derivation of the flow between two flat plates, except that we have to go into cylindrical coordinates. But other than that, the solution is very similar. And then we made a very important generalization. We said, well, this flow, this classical Poiseuille flow that everyone is talking about, is a steady flow. But especially in the body, you as biomedical engineers will have to deal with pulsatile flows that are changing in time. Not just the heart is pulsating, many other things are pulsating. Our breathing motion, our lung is creating pulsating flow, but also as you hear me talking right now, you will have a pulsating flow inside your ear. Acoustic waves generate a pulsating flow inside the cochlea. So we have structures like blood vessels, which are filled with fluid. Blood vessels are filled with blood. And inside that, you have a pulsating blood flow. And that will not have a parabolic profile anymore. It will have profiles like the ones shown here. And this was this Womersley flow solution. A very important flow solution, a very important exact, we're still at exact solutions for biomedical engineering, because this is what occurs mostly inside the human body. So let's put this on our blackboard. So out of the viscous flows, we have the Navier-Stokes solutions. We looked at exact solutions. Just abbreviated word solution, exact solution. And we have examples of Quet, Poiseuille, both plain and Poiseuille in a pipe, and Womersley, the Womersley solution for pulsating pipe. This is what we did in lecture number 4. And then we more or less exhausted what we can do in terms of exact solutions. There's only a limited number of exact solutions, and most technically relevant solutions of Navier-Stokes cannot be written down on a blackboard, are not exact solutions. We need to start simplifying or approximating solutions. And that's what we started doing in lecture number 5, where we looked at Stokes flow. Maybe you remember that movie here. Not sure if it runs. Yeah, I think it runs. Yeah, that was this sort of magic movie where you had this fluid in a cylinder, co-rotating cylinder, or the inner cylinder was rotating, highly viscous fluid and slow rotation. So therefore we had a very low Reynolds number below 1. And we saw that when they put like these fluid markers in it, rotates 4 times in a clockwise direction and 4 times in a counterclockwise direction. You end up with the same configuration again. So there was some kind of reversibility of the flow. And that is a fundamental property of Stokes flow. Sometimes people call it creeping flow. Mathematically speaking, it's the flow at low Reynolds number. I'm also trying to point out what happens, what consequences this flow reversibility has for life at low Reynolds number. There was this paper by Purcell on, I think it was a talk that he gave some 20, 30, I think, well, more like 40 years ago, on life at low Reynolds number. Maybe you remember the scallop theorem. Just expect that you could be asked during the exam to explain to me what the scallop theorem means, why scallops can or cannot move the way they move, why a one-hinged organism has problems moving at low Reynolds number, why not. Maybe you remember that movie that we looked at. I think it was G.I. Taylor who showed a few examples like a flapping floating object and a floating object with a like a corkscrew, a tail that was rotating, and one was moving and one was not. I think these are important concepts to understand in the context of Stokes flow. And then we also looked at technically a very relevant problem, and it's the Stokes drag of a sphere. And this is especially relevant now at times of COVID-19, of infections, maybe, who knows, through aerosol particles. These aerosol particles are actually little droplets, little spheres floating in air, and they adhere to the laws of Stokes drag. Whether they fall or settle or do not settle, how they are transported is governed by this simple law, d equals 6 pi times mu times a times u. And we took this law for this Stokes law for drag, and we derived a drag coefficient. And as we expected from Buckingham pi, the drag coefficient is only a function of the Reynolds number, namely 24 over Ray. This was our maybe first very practical result where we could write down a drag coefficient in terms of the Reynolds. So this is what we did for Stokes flow. Let me put this on the blackboard again. So Stokes flow, let me put this here maybe on the left to see this is like the lowest Reynolds number. So that was Stokes flow. We had the topics of reversibility, Stokes drag, and a few more, huh? And that was lecture number 5. Low Reynolds. Right. Reynolds less than 1 or a lot less than 1. Okay. So we have one extreme, very, very low Reynolds numbers, which occurs quite often actually in biomedical flow problems. And then we looked at another phenomenon, which was sort of on the opposite side. It was for maybe not very large, but for considerably or moderately large Reynolds numbers. Also very large, but it starts already at the Reynolds numbers of, let's say, 10 to 100. We start to get the phenomenon of boundary layers. Let's see what we did here on the boundary layer problem. Here, boundary layers. And if we start talking about boundary layers, we quickly found that there's many, many boundary layers, and there's not a single boundary layer that explains it all. But we looked at one in particular, and it was the Blasius boundary layer, which is maybe the mother of all boundary layers. Also historically, we looked a little bit at the history of how Prandtl came up with these boundary layer equations, how Blasius solved them, how they used concepts of self-similarity of solutions, and just a lot of gut feeling to develop these wonderful solutions, which are quite prototypical. I mean, all the effects, maybe not all, but all important effects of boundary layers are already contained in this Blasius boundary layer. We, for instance, saw that it's growing in thickness, which is very typical a property of boundary layers, not all boundary layers, but of many boundary layers. And we also looked at the drag, the friction drag created by boundary layers, and we again casted it in a non-dimensional form to come up with the drag coefficient, which again is a function of the Reynolds number. So let me switch back. Just as here, the drag coefficient was 24 over Reynolds. Here it was 1.33 over the square root of Reynolds. But still, it's a function of Reynolds. I think I create a few slides with a bunch more drag coefficients for slightly modified boundary layers. By the way, remember these boundary layers are all laminar boundary layers. Turbulent boundary layers came a few lectures later on. Yeah, so this was the Blasius boundary layer, the mother of all boundary layers. Maybe we made at least one extension that we looked at more closely, and it was the Faulkner-Scan family of boundary layers, which explain how a boundary layer changes from the upwind side to the downwind side of, let's say, a blunt object, where the flow is accelerated because it has to go around an object on the upwind side, and how it has to decelerate again when the body closes on the downwind side. And this acceleration and deceleration led to a deformed velocity profile. The profiles on the upstream side had a more, what's called a fuller velocity profile. We're also talking about the favorable pressure gradient. On the other side, on the downstream side, which creates a so-called adverse pressure gradient because it's holding back the flow. It's not accelerating, it's decelerating it. That's what's called an adverse pressure gradient, is creating a velocity profile that eventually gets an inflection point. So we have a curved profile. And there's one critical point where the gradient at the wall goes towards zero. So we end up with a point where we have zero velocity gradient at the wall. And we know that up there, right? The shear stress is proportional to the velocity gradient. So if the velocity gradient becomes zero, there's no shear stress at the wall. Okay, so there's one point with zero shear stress. And if we go beyond that point, we see this here on the right side, the flow may even go in the opposite side, and we get a reversed flow. And in this reverse flow region, we talk of flow separation, because the main flow going from left to right is separating from the wall and goes above this region down here, which is usually called recirculation zone. Or sometimes if it's closing again, people talk of a separation bubble, where we have flow going in upstream direction close to the wall. And that one point where the gradient is zero or the wall shear stress is zero is one particular point. It's called the separation point, usually marked by an S. Okay. We looked at a few more boundary layers toward the end of that lecture. 3D boundary layers, I think also the asymptotic suction boundary layers, just to give you an idea that there's many, many different boundary layers, some with very peculiar properties. But I think if you understand the two main boundary layers, you have already understood quite a lot. So let me put this on the blackboard as well. A lecture on boundary layers. Here, so we have enough space here. Layers, which I'm not going to mark it now. Glasses, Faulkner scan, and so on. We're in there, and that was lecture number 6. Lecture number 6. Stokes flow exact solutions and boundary layers. These were all lectures on incompressible viscous flows. What came next was quite a big jump, and maybe let me just look. Yeah, maybe that's a good moment to make this big jump, to take a little break now. Let me just take a 15-minute break, and then we're going to continue with the next topic that we covered, and that is potential flow, which is not on that side anymore, not on the viscous side anymore, will be on the inviscid side now. We're neglecting viscosity, and then we can talk about potential flows. But that will do after the break, so in 15 minutes.